Hi anyone. Let me first thank the organizers for the opportunity to speak in this conference. I will talk about a long neck principle for Riemannian spin manifolds with positive scalar curvature. I will present some metric inequalities on manifolds with boundary, which are directly inspired by ideas recently proposed by Gromov. Here is the outline of my talk. In the first part, I will review the Dirac operator technique, which is the main method used to study metrics of positive scalar curvature on manifolds with boundary. In the second part, I will discuss some questions and conjectures recently proposed by Gromov regarding metrics of positive scalar curvature on manifolds with boundary. In part 3, I will present some metric inequalities which at least partially address these questions in the spin setting. Finally, in the last two parts, I will describe the analytic machinery that I used to obtain such inequalities. We start with the Riemannian manifold M with Riemannian metric G. The scalar curvature of G is a smooth function on M, which is constructed out of the Riemann curvature tensor. It is the weakest curvature invariant that can be attached to a Riemannian manifold M. Moreover, the existence of metrics of positive scalar curvature on a manifold M is related to its topology. Now I want to focus on the case when the manifold M is endowed with a spin structure. So let's M be a closed Riemannian spin manifold, let A be a sister algebra, and let E be a bundle of finitely generated projective Hilbert modules with inner product and metric connection. When A is the algebra of complex numbers, E is a vector bundle. We denote by Z the spin Dirac operator twisted with the bundle E. Here S is a spinor bundle associated to the Riemannian spin manifold M. The operator Z is a first-order elliptic differential operator of order 1, and is related to the scalar curvature of the metric G through the classical Lichner-Horowitz formula. In this formula, the first term on the right-hand side is the connection Laplacian, which is a non-negative differential operator of order 2. The second term is 1/4 the scalar curvature of the metric G. And the third term is an endomorphism of the bundle S tensor E, which depends linearly on the component of the curvature of the connection on the twisting bundle E. In particular, if the connection on E is flat, then the endomorphism R vanishes. Since M is closed and Z is elliptic, then the index of Z is well defined and encodes topological information. The main case to keep in mind is when M is an even dimensional closed spin manifold and G is a Riemannian metric on M and E is a vector bundle on M with a Misha connection. In this case, the spinor bundle is C2 graded, and moreover, the C2 grading of the spinor bundle induces a C2 grading of S tensor E in the obvious way. And in this case, the twisted Dirac operator is odd with respect to this grading, which means that it has this form. So here, Z plus is an operator mapping smooth sections of S plus tensor E into smooth sections of S minus tensor E, and similarly Z minus. And moreover, the operators Z plus and Z minus are formally adjoint with each other. Now, since the manifold M is closed, and the operator Z is elliptic, then the kernel of Z plus and the kernel of Z minus are finite dimensional vector spaces. Therefore, the difference of their dimension is a well-defined integer, which is by definition the index of the operator Z. By the TS single index formula, this integer can be expressed by integrating a certain cohomology class or the manifold M. So this is the check character of E, and this is the head class, which is a certain polynomial in the Montragin number. The main point here is that the twisted Dirac operator Z depends on the choice of a Riemannian metric on M and of an Hermitian connection on E, but its index is independent of the choice of G and the connection on E, and this follows exactly from the T-Singer index formula. So in other words, all these objects are independent of the choice of a metric G and an Hermitian connection on E. Now we get back to the general situation. In this talk, we will make use of the following fact. So if Z squared is uniformly positive, then the operator Z is invertible, and therefore its index must vanish. From the Lichner-Horowitz formula, we deduce the following inequality, and which implies that when the index of Z is non-zero, then the scalar curvature of G cannot dominate 4 times the endomorphism R. So in other words, index of Z non-zero dictates a balance between the scalar curvature and the curvature of the connection on the twisting bundle. When E is flat, the endomorphism R vanishes, and if the index of Z is non-zero, then there are no metrics of positive scalar curvature on M. In this talk, we will focus on 2 cases. The first case is when E is a vector bundle, or equivalently, the C-star algebra A coincides with complex numbers. In this case, the index of Z is an integer. The second case is when A is equal to C-star gamma, which is the group C-star algebra of the fundamental group gamma of M. This is a completion of the real or complex group algebra of gamma. We take E to be the Mishenko bundle over M. The Mishenko bundle has typical fiber the group C-star algebra of gamma, and is endowed with a canonical flat connection. It encodes information coming from the fundamental group of the manifold M. Notice that here, to be precise, the typical fiber of the Mishenko bundle is a free rank 1 module over C-star gamma. In this case, the index of Z is an element of the K-theory of C-star gamma, and is called the Rosenberg index of M. Since the Mishenko bundle is flat, the endomorphism in the Lichner-Horowitz formula vanishes, and the Rosenberg index is an obstruction to the existence of positive scalar curvature metrics on M. And actually, this is the most general known index obstruction to the existence of metrics of positive scalar curvature on a closed spin manifold. In this talk, I will focus on manifolds with boundary. When X is a compact Riemannian manifold with boundary of dimension at least 2, it is well known by a classical result by Gromov that X carries a metric of uniformly positive sectional curvature. And then a fortiori, it carries a metric of uniformly positive scalar curvature. Therefore, in order to use topological information to study metrics of positive scalar curvature on X, we need extra geometric conditions. When X is equipped with a Riemannian metric with a product structure near the boundary, it is well known by classical results of Atiyah, Patodi, and Singer that the Dirac operator with global boundary conditions is elliptic. In this talk, I will not make any assumption on the structure of the metric near the boundary, and I will assume that the topological information is stored away from the boundary. More precisely, I will present some metric inequalities following the point of view recently proposed by Gromov. I now want to discuss some questions recently proposed by Gromov regarding metrics of positive scalar curvature on manifolds with boundary. Suppose that X is a compact oriented and dimensional Riemannian manifold with boundary, and suppose that F is a smooth area decreasing map from X into the sphere. Then the length of the neck of XF is the distance between the support of the differential of F and the boundary of X. In this picture, the blue region is the support of the differential of F, and the red region is the neck of XF. In other words, the red region is sent by the map F into a point in the sphere. The long neck problem consists in the following question. What kind of a lower bound on the scalar curvature of G and a lower bound on the length of the neck of XF would make degree of F equal to 0? More precisely, Gromov conjectured the existence of a positive constant Cn depending only on the dimension n of the manifold X, such that if scale G dominates the scalar curvature of the round sphere and the length of the neck is greater than the constant Cn, then the degree of F must be 0. In other words, if scale G is greater or equal than n times n minus 1 and the degree of F is non-zero, then according to this conjecture, we obtain an upper bound for the length of the neck. Observe that the assumption that the map F is area decreasing is fundamental here. The reason is that given any oriented manifold X of dimension n, it is always possible to produce a degree 1 map F into a sphere which is constant outside of a small disk. So in other words, the existence of degree non-zero maps into the sphere cannot tell us much about the geometry of the manifold X. Also notice that if X has a metric of positive scalar curvature which has a product structure near the boundary, then according to this conjecture, there is no map F from X into the sphere which is constant in the neighborhood of the boundary and satisfies those three properties. The reason is that if the metric has a product structure near the boundary, then I can stretch the neck as much as I want, and therefore there cannot be any upper bound for the length of the neck. We now consider a second question that is again related to the length of the neck of a manifold with boundary. We consider the following geometric setting. Let Y be a closed n-dimensional manifold. Let X be the n-dimensional manifold with boundary, which is obtained by removing a small n-dimensional ball from Y. Let G be a Riemannian metric on X. For a positive constant R, which is small enough, let BR be the geodesic color neighborhood of the boundary of X of width R. In this picture, the manifold with boundary X is obtained from the closed manifold Y by removing a small n-dimensional ball. This is the boundary of X, and the highlighted region is the geodesic color neighborhood of the boundary of X of width R. In this situation, Gromov made the following conjecture. Suppose that Y minus a point admits no complete metric of positive scalar curvature. Moreover, suppose that the scalar curvature of G is bounded from below by a positive constant sigma. Then there exists a positive constant C independent of the manifold, such that the width of a geodesic color neighborhood of the boundary of X must be smaller than C over the square root of sigma. Notice that the larger is the lower bound of the scalar curvature of G. The smaller is the upper bound of the width of a geodesic color neighborhood of the boundary of the manifold X. Observe that if Y is a closed n-dimensional manifold with n at least 3, which admits a metric of positive scalar curvature, and we embed a small n disk into Y, then by classical results of Gromov-Lawson and Schoen and Yao, there exists a metric of positive scalar curvature on Y, which has a product structure near the boundary of the embedded disk. And this means that Y minus a point admits a complete metric of uniformly positive scalar curvature. And therefore, in this case, there cannot exist a positive constant satisfying this condition. Now, let us finally discuss a third question that is again related to the neck of a manifold with boundary. So we suppose that N is a closed manifold, and well, a band over N is a manifold V, which is diffeomorphic to N times a segment. Suppose that G is a Riemannian metric on V, and then in this case we say that V is a Riemannian band over N, and we define the width of V as the distance between the two boundary components. In this situation, Gromov made the following conjecture. Suppose that N is a closed manifold of dimension at least 5, which does not admit a metric of positive scalar curvature. Suppose that V is a Riemannian band over N, whose scalar curvature is bounded from below by a constant sigma greater than 0. Then the width of V, which is the distance between the negative and positive boundary component of V, is smaller or equal than 2 pi times the square root of n minus 1 over sigma n. Let me remark that Gromov established this conjecture for the n-torus using the minimal hypersurface technique. Let me also remark that the assumption that N does not admit a metric of positive scalar curvature is fundamental here. Otherwise, there exist Riemannian bands over N with arbitrarily large width. And to see that, just consider the product metric over a cylinder. Observe that in all these questions by Gromov, the topological information is localized in a region inside the manifold, and the geometric information is formulated in terms of a lower bound of the scalar curvature and the distance between the boundary of the manifold and the topologically relevant region. It is natural to ask whether these questions can be at least partially addressed in the spin setting using the Dirac operator technique. The method presented in this talk is based on the analysis of the spin Dirac operator on the incomplete Riemannian manifold, which is obtained by removing the boundary from a compact Riemannian manifold with boundary. I will assume that the topological information is encoded by bundles which are supported in the interior of the manifold X. I will first present the main inequalities, then I will describe the analytic machinery I used to obtain these inequalities. For the first theorem, let X be a compact n-dimensional Riemannian spin manifold with boundary. And let F be a smooth area decreasing map from X to the n-sphere. Moreover, suppose that the scalar curvature is bounded from below by a positive constant sigma on X, and that the scalar curvature dominates the scalar curvature of the n-sphere on the support of the differential of F, and that the length of the neck is greater than pi times the square root of n minus 1 over n sigma. Then if these hypotheses are satisfied, then the degree of f must be 0. For the first assumption, notice that we allow the scalar curvature of G to be smaller than n times n minus 1 on the neck of the manifold. And then in this case, the neck can be possibly longer. Notice that if the scalar curvature is greater or equal than n times n minus 1 on x, and the degree of f is not 0, then the length of the neck is smaller or equal than pi over n. And this addresses the long neck problem in the spin case. Let me also remark that if M is a complete n-dimensional Riemannian spin manifold, and F is a map into the sphere, which is locally constant at infinity and has degree non-zero, and moreover suppose that the scalar curvature is greater or equal than n times n minus 1 on the support of the differential of f, then by results of Gromov-Lawson and the rule, the scalar curvature cannot be uniformly positive. This result has been recently improved by Zhang, who proved that actually scale G cannot be positive. Theorem A implies the first of those two results, but not the second one. I now want to formulate a higher version of theorem A. We consider the following geometric setting. Suppose that Y is a closed n-dimensional spin manifold with fundamental group gamma. Moreover, suppose that L is the Mishenko bundle over Y. Remember that this is a bundle with a typical fiber sister gamma, which is the group sister algebra of gamma. We denote by alpha Y the Rosenberg index of Y, which is the index of the Dirac operator twisted with the Mishenko bundle. We also consider the trivial bundle over Y with typical fiber sister gamma. We now consider the class of closed spin manifolds satisfying the following condition. We suppose that the Rosenberg index does not coincide with the index of the spin Dirac operator on Y twisted with the trivial bundle with typical fiber sister gamma. The intuition is that there is a discrepancy between the higher index and the lower index. Manifolds satisfying condition H different from L form a rich class. For example, all closed enlargeable spin manifolds satisfy this assumption. And this is due to results of Hanke and Schick. I will not discuss the notion of enlargeability here. This is a notion due to Gromov and Lawson, and I refer to their papers. But I want to point out that some interesting examples of enlargeable spin manifolds are the n-torus and any closed spin manifold which emits a metric of non-positive sectional curvature. Moreover, if M1 and M2 are closed spin manifolds and M1 is enlargeable, then the connected sum is enlargeable as well. And in this way, we can already construct many examples. Finally, observe that a closed simply connected spin manifold does not satisfy the condition H different from L. Now consider the same setting as in conjecture A by Gromov. So in other words, we suppose that Y is a closed n-dimensional manifold, and then X is the n-dimensional manifold with boundary, which is obtained by removing a small n-dimensional ball from Y. We put a Riemannian metric on X, and for R small enough, we consider the geodesic Kolar neighborhood of the boundary of X of width R. Then in the situation described above, suppose that Y is spin and satisfies the condition H different from L, and moreover suppose that the scalar curvature is greater or equal than a positive constant sigma, then the width of the Color neighborhood must be smaller or equal than the constant pi times square root of n minus 1 over n sigma. So in other words, this theorem states that under this condition, there is a upper bound for the width of the Color neighborhood of the boundary. And then in the next theorem, we show that if Y is a closed spin manifold satisfying the condition H different from L, then Y minus a point admits no complete metric of positive scalar curvature. And now, putting together theorem B and theorem C, we deduce that conjecture A by Gromov holds for all closed spin manifolds satisfying condition H different from L. For the last result that I want to present in this talk, we consider a closed n-1 dimensional manifold N with fundamental group gamma. Now suppose that the Rosenberg index does not vanish, and let D be any Riemannian band over N whose scalar curvature is bounded from below by a constant sigma greater than 0. Then the width of a band, which is, remember, the distance between the two boundary components, must be smaller or equal than 2 pi times the square root of n minus 1 over sigma n. And observe that this theorem implies that conjecture B holds for all closed spin manifolds with non-vanishing Rosenberg index. Let me remark that under the same hypothesis of theorem D, Zeitler proved that there exists a constant C such that the width of the band V is more or equal than C over the square root of sigma. On the other hand, Gromov proved that the constant 2 pi times the square root of n minus 1 over sigma n is optimal. Therefore, the constant that we find in theorem D is sharp. I now want to outline the analytic ideas that I use to obtain these inequalities. I will discuss theorems A and B. The other theorems can be obtained with similar techniques. We consider the following setup. Let X be a compact Riemannian spin manifold with boundary. By removing the boundary, we obtain the open manifold X naught. The metric G induces any complete metric on X naught that we denote by the same symbol. Let W be a bundle of finitely generated projective Hilbert modules over X naught, and let Z be the Dirac operator twisted with a bundle W. Notice that Z is a formally self-adjoint elliptic operator of order 1. We regard Z as an unbounded symmetric operator on L2 with initial domain, the compactly supported sections of the bundle S tensor W. The problem is that since the manifold X naught is not complete, the closure of the operator Z is not self-adjoint. In order to solve this problem, I will make use of a rescaling trick that I will now present. We make the following construction. Let delta be the distance function from the boundary. In a geodesic Color neighborhood of the boundary, delta is smooth and its differential as norm 1. Pick a constant r prime between 0 and r, and let gamma be a smooth function such that gamma t is equal to the square root of t in a neighborhood of 0 r prime, and gamma is constant in a neighborhood of r infinity. Here is the picture. Let rho be the smooth function on X naught, defined as the composition of gamma with delta on the Color neighborhood BR, and which is constant outside of BR. We now use the function rho to rescale the Dirac operator z. More precisely, we consider the rescaled operator z rho, which is defined as the composition rho z rho. Observe that z rho is a first-order elliptic formally self-adjoint differential operator. We regard z rho as an unbounded operator on L2 with initial domain that compactly supports smooth sections. The next proposition states that z rho has the wanted analytic properties. More precisely, the closure of the operator z rho is self-adjoint and regular. The notion of regularity, which I will not discuss here, is a technical condition which is needed if we want to do index theory in the C-star algebra setting. Let me also point out that this proposition follows from the theory of manifolds which are complete for a differential operator. This theory was developed by Hickson and Rowe and has been recently extended by Ebert to the C-star algebra setting. I now want to use this rescaling trick to develop index theory on the open manifold X0. Let me first explain how to encode topological information. Suppose E and F are bundles of finitely generated projective Hilbert modules with inner product and metric connections over X0. We now make the same assumption as in the classical work of Gromov-Lawson. We assume that the bundles E and F have isomorphic typical fibers and are trivializable at infinity. This means that there exists a finitely generated projective Hilbert module nu and a compact subset K, such that the bundles with connections E and F are isomorphic to the trivial bundle with typical fiber nu endowed with a trivial connection outside of the compact set K. In this case, we say that K is an essential support of EF. In this setting, we define a relative index following Gromov-Lawson. So we let L be a smooth compact submanifold with boundary whose interior contains an essential support of EF. So here is the picture. So K is essential support and L is a manifold with boundary whose interior contains K. We now form the double of L by gluing L and L minus along the boundary of L. Here L minus denotes the manifold L with opposite orientation. We construct the bundle with connection V by gluing the bundle E over L and the bundle F over L minus along the boundary of L. Observe that the bundle V is well defined by the Gromov-Lawson assumption. Notice also that the double is endowed with a spin structure which is induced by the spin structure on L and the spin structure on L minus. We define the relative index of the pair EF as the index of the Dirac operator on the double twisted with the bundle V. Here, it is not difficult to see that the index of this operator does not depend on the choice of a submanifold with boundary L, whose interior contains an essential support of the pair EF. And therefore, the relative index depends only on the bundles E and F. The question now is how to construct a Fredholm operator on X0 whose index coincides with the relative index of E and F. To this end, we fix a rescaling function rho and consider the rescaled twisted Dirac operators Q rho and R rho. For example, Q rho is defined by first twisting the Dirac operator with the bundle E and then by rescaling it with the function rho. The problem is that the Lichtenauer formula for the operators Q rho and R rho is quite complicated. And in particular, the positive term coming from the condition that the scalar curvature is uniformly positive is not enough to control the negative term coming from commuting the Dirac operator with the rescaling function rho. In other words, the fact that the scalar curvature is uniformly positive does not imply that the operator Q rho and R rho are uniformly positive at infinity. The idea is that to fix this problem, we make use of a potential to construct an operator which is uniformly positive at infinity. Let S plus S minus be the Z2 grading of the spinor bundle of X naught. It induces Z2 gradings of the twisted bundle S tensor E and S tensor F. Observe that the operators Q rho and R rho are odd with respect to its grading, which means that they have this form where Q rho plus and Q rho minus are formally adjoint to each other, and the same is true for R rho plus and R rho minus. We now fix a compatible potential, which is a smooth function phi over X naught, such that phi is equal to 0 in a neighborhood of an essential support of EF, and phi is constant and non-zero in a neighborhood of infinity. Here I drew a picture where K is an essential support of EF, phi is 0 in a neighborhood of K, and phi is constant and non-zero in a neighborhood of infinity. By the Gromov-Lawson assumption, phi defines bundle maps phi from S plus tensor E to S plus tensor F, and so on and so forth. This is due to the fact that outside of K, the bundles E and F are isomorphic. Now we define the bundles W plus as S plus tensor E plus S minus tensor F, and W minus as S plus tensor F plus S minus tensor E. Now we define the operator P plus from smooth sections of W plus to smooth sections of W minus using this formula. Denote by P minus its formula joint, and consider the graded bundle W defined as W plus plus W minus. The generalized Gromov-Lawson operator associated to our data is the operator P acting on smooth sections of the bundle W, defined as through this formula. By construction, P is an elliptic formally self-adjoint operator of order 1. By the discussion about the rescaling function rho, the closure of this operator is self-adjoint. The next theorem states that the operator P squared is uniformly positive at infinity. The previous theorem implies that the operator P is Fredholm, and therefore its index is well defined. We interpret the index of P as the analytic index and the relative index as the topological index. The next theorem states that the analytic index and the topological index coincide. Here, I want to remark that it is possible to define generalized Gromov-Lawson operators on every open manifold M. Of course, with a suitable choice of a rescaling function rho, depending on the geometry at infinity of the manifold M. So far, we discussed the case when M is the interior of a compact Riemannian manifold with boundary. When M is a complete Riemannian manifold, then the Dirac operator is essentially self-adjoint, and we can choose rho to be equal to 1. In other words, we don't need any rescaling. In this case, our construction yields the construction of Gromov and Lawson. In other words, the analytic construction presented here is a generalization of the construction of Gromov and Lawson in the case when the metric is not complete. We now describe two examples of bundles satisfying the Gromov-Lawson assumption. The associated generalized Gromov-Lawson operators are used to prove theorems A and B. For the first example, we start with a compact Riemannian spin manifold with boundary X. And we let F be a smooth map from X into the sphere, which is constant near the boundary. Here I drew our familiar picture where the blue region is the support of the differential. The red region is the neck of the manifold, which is sent by the map F into a point of the sphere. Now we let E0 be a vector bundle with Hermitian connection over the sphere, such that the pairing of the Chern character of E0 with the fundamental class of the sphere does not vanish. We now use the map F to pull back the bundle E0 to the manifold X. In this way, we obtain a bundle with connection E over F, which is trivializable outside of the support of the F. In other words, over this red region. Now we let F be the trivial vector bundle of the same rank as E, which is equipped with a trivial connection. Now observe that the bundles E and F, when restricted to the interior of X, satisfy the Gromov-Lawson assumption. The associated generalized Gromov-Lawson operator is used to prove theorem A. More precisely, in order to prove theorem A, we make use of the following two properties of the bundles E and F. First of all, if F is area decreasing, then by results of the rule, the endomorphism R is greater than minus n times n minus 1 over 4. Here, R is the endomorphism associated to the connection on E that appears in the Lichner-Horowitz formula. Moreover, if the degree of F is non-zero, then by results of Gromov-Lawson, the relative index of EF is non-zero. We now consider a second example. Let Y be a closed spin manifold. Let X be the manifold with boundary, which is obtained by removing a small ball by the manifold Y. Now we put a Riemannian metric G on the manifold with boundary X. Now suppose that E is the Mishenko bundle trivialized near the geodesic color neighborhood BR, and let F be the trivial bundle with fiber C star gamma equipped with a trivial connection. And now observe that the pair EF, when restricted to the interior of X, satisfies the Gromov-Lawson assumption. The associated generalized Gromov-Lawson operator is used to prove theorem B. More precisely, to prove theorem B, we make use of the following property of the bundles E and F. So suppose that Y satisfies condition H different from L. Remember that this means that there is a discrepancy between the higher index and the lower index. Then in this case, the relative index of EF does not vanish. I now want to discuss a vanishing theorem for generalized Gromov-Lawson operators, which is used to prove theorems A and B. Suppose that the scalar curvature of G is bounded from below by a positive constant sigma. Moreover, suppose that K is an essential support of the bundles E and F, and let nu be a smooth function such that the support of nu sits inside K. Moreover, we suppose that the function nu satisfies those two inequalities. Observe that this means that the function minus nu is pointwise a lower bound for the endomorphisms induced by the connections on the twisting bundles E and F. Moreover, we make the following hypothesis. We suppose that scale G over 4 is greater than nu, and that the distance between K and the boundary of the manifold X is greater than pi times the square root of n minus 1 over n sigma. Then, when these conditions are satisfied, we deduce that the relative index of E and F must vanish. Notice that the first assumption means that the scalar curvature dominates the endomorphisms induced by the connections on E and F. And the second assumption means that the length of the neck of the manifold X is longer than a constant, depending on the dimension of the manifold and the lower bound of the scalar curvature. I now want to give a sketch of the estimate which is needed to prove the vanishing theorem. Observe first that by the index theorem, it suffices to show that the operator p squared is uniformly positive. Therefore, the first step is to estimate the operator p squared from below with a smooth function theta, which depends on rho, phi, and nu. The function theta has a complicated expression, so I will not write it out. The important information for this sketch of the estimate is that the negative part of theta consists in three terms coming from nu, the differential of phi, and the differential of rho. The positive part of theta consists in two terms coming from the scalar curvature of G and the potential phi. We now choose positive constants lambda and eta, with eta smaller than 1, and we use these constants to divide the manifold X into three regions. We let R3 be the region consisting in the points of X whose distance to the boundary of X is at most eta lambda. Let R2 be the region consisting of all points in X whose distance to the boundary is between eta lambda and lambda. And finally, let R1 be the complement of R2 union R3. We choose lambda small enough in such a way that K is contained in the interior of R1. Notice that with this choice, the support of the function nu is contained in the interior of the region R1. Moreover, we choose the rescaling function rho and the potential phi in such a way that the support of the differential of phi is contained in the interior of R2. And the support of the differential of rho is contained in the interior of R3. Now observe that with this choice on the region R1, we have phi equals 0 and rho equals rho 0. Therefore, in this region, we want to use the positivity of the scalar curvature to control the negative term coming from nu. In the region R2, we have that rho is constant and nu is 0. And therefore, in this region, we want to use, again, the positivity of the scalar curvature to control the negative term coming from the differential of phi. And finally, in the region R3, we have that nu is equal to 0 and phi is constant. And now we want to use the potential phi to control the negative term coming from the differential of rho. Then the condition that scale G over 4 is greater than nu gives control on the region R1. So this is basically just the Ricci formula. The condition that the distance between K and the boundary of X is greater than pi times the square root of n minus 1 over n sigma allows us to choose lambda and eta in such a way that the potential phi grows enough in the region R2 to control the negative term in R3 coming from commuting the rescaling function with the Dirac operator. Finally, I want to comment on this specific constant. The term pi comes from the fact that the best choice for phi is a function of this form, where C1 and C2 are constants that depend on n and sigma. The term pi comes from the fact that we want enough room for the argument of the tangent to hit pi over 2. Finally, the term square root of n minus 1 over n comes from the Friedrich inequality that I will next describe. We now consider the following situation. Let M be a Riemannian spin manifold without boundary. Let E be a bundle of finitely generated projective Hilbert A modules with inner product and metric connection over M. Let Z be the spin Dirac operator twisted with a bundle E. Now in this situation, for every compactly supported smooth section of the bundle S tensor E, we have the following inequality. Now recall that the Ricci formula tells you that Z squared is equal to the connection Laplacian plus 1/4 scale G plus the endomorphism R induced by the connection on E. Therefore, the Friedrich inequality is an improvement of the inequality which directly follows from the Ricci formula by the factor n over n minus 1. And this factor is responsible for the term square root of n minus 1 over n in the estimate. This inequality was first proved by Friedrich in the case when M is closed and E is a vector bundle. It was extended to open manifolds by Christian Baer. So what I did here was to extend the result of Christian Baer to the C-star algebra setting. This is all I wanted to say. So thank you very much for your attention.